Hi everyone, welcome back to 165CL. And today we're going to be finishing up that lab module 2, where we're looking at the precipitation hardening in aluminum copper alloys. So the main things we want to do today are we want to use that indentation width data that we obtained in our last module or last lecture to extract out these hardness values for each of those conditions of time versus annealing temperature. We're going to plot this data so that we can understand it and analyze it in terms of what's happening inside of our microstructure. All right, so the first thing we have to do before we put too much weight onto these indents that we've gone in and measured is we want to make sure that there's nothing wrong with these experiments. And one very common thing that can happen is you can have what's called pile up or sink in around an indent. So when we go, and on the left here is showing a little schematic of my material in green and my indent coming down in blue. We're going and looking and pressing on that surface with a known force, and then we're looking at that impression that's left. We're in this process assuming that this contact is just adhering to that surface and the geometry of the contact is unchanged. It is possible to have what's called pile up. It's shown here on the left. It's where your material sort of flows outward and is touching more of that indenter tip than you think it really is. So that's shown here on the bottom below that. The apparent contour is shown in black. You think it's just this indent shape, but since the material is pressed out, there's more contact than you think there is. The alternative situation can happen too, where you have the material sinks in. In this case, it's shown here. So the material kind of sucks in and it's not contacting near the edges like you think it is. And in this case, your true contact area is less than what you imagine it to be. So the effect is that you can either overestimate or underestimate your hardness depending on whether or not you correctly take this into account. Just as another way of seeing this, these indents are slightly different than the sort of four-sided Vickers indents that we're using here. These are from what's called a Berkovich tip, but the idea is very similar. On the left here, you can see pile up where the material is flowing out the sides. And on the right here, you can see that sink in where the material is kind of sucked in. So we can do this sanity check, go and look at our indents. I just took an example. This is from the naturally aged. So the condition just left at room temperature, 20 degrees C for 3 hours. And we could go, for example, and make sure that these edges that are opposite each other are parallel to each other, okay? If we had pile up or sink in, that wouldn't be true. But if you go and check your indents, find that that's okay, okay? So we were careful, we checked that out, and we're able to move on. The next thing we want to do is go and start taking those length measurements we took from the indents and using them to extract some values of hardness. I'm going to use the as received data in my slides right here, but remember we have an Excel sheet posted with all the data from the as received and then annealed under different temperatures for different times. So the basic idea of hardness is we're going to come and press down with a known force, and by looking at and comparing the indents, we can tell what's the strength of my material. All right, in this little schematic here, it's just showing for the same force, if I get a bigger indent, then that means my material is softer or less hard, okay? But the main thing I wanted to point out in this case is that in each situation or for each indent, we went and took 2 measurements. So we measured the diagonals along each direction, but really what we want is to be able to say, what's the size of each individual indent, okay? So what we actually want to do is take and use these values. So there's 5 indents where each time I took 2 measurements, and we're going to average those to get a measurement of the diagonal length for each of those indents. Really, if everything was perfect, you would expect that indent shape to be perfectly symmetric and both those measurements to be the same. Small things that can come in and cause issues are primarily things like if your surface is not exactly flat, so if it's tilted a little bit, you can get some deviation from the expectation. If the indenter tip is not the perfect shape, so if it's worn away over years of use or something like that, that can give you some variation. Now, these values are actually pretty good. They're very, very similar to each other. So this isn't a major problem, but it's just a sort of way we go in and extract one value for each indent. All right, so our next step, I'm sort of updating this table. So I went from just having these two individual lengths. Now I have the average length shown here in that final column. We're going to use this to calculate our Vickers hardness. So hardness is defined pretty simply. It's just the force that we're applying divided by that contact area. Okay. Now that force is known from our experimental design. When we went through, we said we're going to do these indents at 50 grams force. Okay, great. That area is actually what we're going to go and calculate. Now, we have the information we need. The first sort of clue or thing we're going to use is this average length, but we're also going to use the fact that we know the geometry of that indenter. Okay, so this Vickers indenter has a very specific shape. It has this pyramidal shape with four sides, and there's this 136-degree angle between the opposite faces. So we can use that and go and calculate what the area of that contact area is, depending on that measurement we took after the fact of that impression length. And we'll find that this area is going to be L squared divided by some number 1.8544. This approximately is just there because it's not exactly 1.8544, it's 1.8544, 12876, a bunch of numbers going. In any case, we can go and then say that our hardness is going to be 1.8544 times the force applied divided by that diagonal length squared. Okay. Now, the one thing we do have to make sure we do is check what the usual units are of Vickers hardness. So the typical units that are used are kilograms force divided by millimeters squared. So that means we need to make sure that the numbers we're plugging in there have the correct units as well. So if I go up, our lengths we have, they're in millimeters, so that's fine. The force, we said it was 50 grams force. We want to make sure to convert that to kilograms force. So divided by 1,000, it's 0.05 kilograms force. So with that, you can go and plug in and add another column to your data. So got the average length, and now I'm plugging in, getting a Vickers hardness measurement for all 5 of those indents I took. Now you can notice that they're not all exactly the same. That's okay. Maybe I'm probing slightly different little areas of my microstructure. So our next step is to take these individual measurements we have, and we're going to calculate statistical properties for each condition, okay? Now, all I mean is really I want to go and find what's an average hardness for, in this case, my as received condition, and also what's the standard deviation on that value. So I take those 5 measurements. I'm going to find that my average hardness is 99. My standard deviation is 12.8. And usually you'll see Vickers hardness values just reported as the number without the units. We're just doing a sanity check and remembering that these values technically have the units of kilograms force divided by millimeters squared. Okay, so just if you hear somebody describe Vickers hardness without giving the units, they're implying these basic ones right there. So now that we have all this data, we can go and we can start to plot things as a function of time and understand what's happening in these experiments. Okay, I just want to note I'm showing you this for the data, the calculations I did. That procedure I just did for the as received data, I'd like you to go and do it for all of the time and temperature points. Okay, so calculate those values yourself, and please also plot them yourselves. In our last lab module, I showed you a way of plotting data with MATLAB. I know people use other things, so in this case, I just went and made some plots with Excel. So you can use whatever plotting software you like and you're comfortable with. It doesn't really matter. Just want to make sure that we get practice analyzing the data ourselves. Okay, so on the left here, I'm showing a plot of Vickers hardness on the Y versus time on the X. And you can see we go all the way up to 168 hours. That's my 1 week time point at the natural aging. And on this, you can see the blue is the 20 degrees C or natural aging. The orange is 150 degrees C, and the red is 200 degrees C, annealing treatments. You can notice that this data is a bit squished towards the left side of the plot. So just briefly, so we could look at that, what I did is I truncated this data at 30 hours. So now that final 1 week time point in the blue data set is off the chart, okay? But we're just looking at the shorter times. And you can see that in all cases that these samples are getting harder or stronger with time. And in the case of the red, the data actually starts to fall down and the material gets weaker over time. Okay? So really neither of these ways is optimal for looking at and visualizing this data. Oftentimes, if we have big variations in one value on an axis, so in this case, it's time, the way we can visualize this a little bit better is instead of on a linear scale, where each movement to the right moves us 1 unit, maybe 1 hour or something like that, we're going to use a logarithmic scale. So I went and took the same data, and I just made my x-axis logarithmic, okay? Now, I will note I'm not plotting the 0 time point here because it's difficult to plot things at 0 because you're doing a logarithmic axis. You get smaller and smaller and smaller, but you never hit 0, okay? So that's my same data point. I would put a line on here to denote time equals 0. So that's where all the data points started. And in this case, I also put a line at 99 Vickers hardness. So that's our as received data. So you can start to get a better sense and see all the data together. So for example, my naturally aged at room temperature sample increased from a little bit over 80 Vickers hardness and is approaching the value characteristic of that as received sample. My intermediate temperature sample is actually stronger after 1 day of annealing than the as received sample. And my 200-degree annealed sample was stronger, but because I kept annealing it for too long, it ended up being the weakest of the bunch by the end of the experiment. Okay. So the last thing you could go and do is go and show those error bars on your data. So here I just went and put Y error bars. These are showing my one standard deviation up, 1 standard deviation down on my data. It looks a bit messier, but it can allow us to sort of see where the mean and the standard deviation, the whole distribution is moving, okay? And for example, that's important because it tells you when to sort of acknowledge differences in that data as being statistically relevant, okay? Just as an example, if you look at this blue curve, it shows me that my material is stronger, stronger, weaker, stronger, and then stronger and stronger, okay? It probably didn't really get weaker there. It's just that I have limited data points for each of those times, and it probably, within the error bars, it probably went up a little bit and it had some sort of smooth behavior, okay? Now, in contrast, I can look at and say, well, this sample at the end of my red data is a lot lower than it was after 5 hours. It's outside of the error bars, and it's a real change. It really has gotten softer in that case. So the last thing for us to do is sort of start to rationalize these trends in terms of what's actually happening to our microstructure and what's going on inside of our material. Just as a reminder, we talked about a lot of different transitions. We talked about going from a solid solution to small clusters of solute, to coherent precipitates, to incoherent precipitates, and then finally those precipitates coarsening. And we go from left to right on this plot as we have longer and longer aging time, okay? That's true for any given temperature. Now, the rate at which these happen can depend on the annealing temperature, right? So maybe these happen faster if I'd use a higher temperature. When we're thinking about mechanical properties, we want to sort of think about also how much of these different things are inside of our material. So although those are all evolving, those first 3 steps, going to solute clusters, going to coherent and then incoherent precipitates, are really where we're nucleating new obstacles, okay? So we're adding more and more things that can get in the way of the dislocations. In contrast, this final part, this coarsening, is generally where we're just growing existing obstacles. Now, if we remember what we learned from lab module 1, that being in a given place on the phase diagram tells us that we're going to have a certain weight percent of our second phase. In this case, our second phase are these precipitates. If that weight percent of the precipitate stays the same, but they're getting bigger, that means that they have to be sort of further apart, or their density is going down. So if you want to think about it, before these precipitates coarsen, there's lots of little precipitates everywhere, and that's lots of different obstacles for that dislocation. Once they keep growing, there's going to be, maybe instead of 100 small obstacles, there's going to be 2 big blobs of that same phase. That's actually not that great for strengthening, because remember, the stress needed to get past an obstacle is proportional to the inverse of that spacing. So what we really want is really small spacing for really high strength. So a sort of schematic you can draw for general aging behavior, this isn't even putting any numbers on these axes, but it's something that looks like the data we have from this module. It's our strength and our hardness on the Y, our aging time on X, and it actually has in terms of the logarithm. So it's connecting to how we actually looked at our data, is that this early stage, this is where you're going from a solid solution. So you have 0% of your second phase to whatever percent your phase diagram tells you. This is where you're increasing along this whole range. Now, another interesting point is that it doesn't have to be some sort of monotonic increase. So in this case, you can have an increase. It doesn't really increase very much. It kind of stays stagnant, and then it gets much higher, okay? And then eventually, you start to see your strength or your hardness fall off. And that's indicative of the fact that you have the same fraction, whatever percentage is told you by your phase diagram, but it's now arranged in different sizes and distributions inside of your sample, okay? So it's important to sort of keep these pictures on this slide and the one before in mind as you're describing and discussing your data. So you can think about describing what's happening inside your material when you talk about what's the best temperature for having this precipitation hardening behavior happen, what's suboptimal, and sort of why each of those are true. Okay, all right. So that's the end of our lab module 2. You have until the end of next week to write your lab report. And as usual, Yunfei and I will be in the working sessions, happy to answer any questions you have. All right, have a great day, and I'll see you soon.